gone. It's like, did you make a mistake or is the eye actually gone?
Was there another I and it turned into a -1?
Okay, new class is starting. Okay, so the first thing is exam 3 is Friday. And the topics are everything up through the second law, and entropy. So none of this Rankine cycle stuff that we've been doing for a little while. Anybody have any questions about the test? Okay. Anybody have any homework questions? I assigned.
Number 3.
Did you assign 2 and 3 then?
Not 2 yet, because that has superheat in it.
Oh, but then 3 was due today. Is that?
No, just I think 1 was due today and 3 is. Is that right?
Well, 1 is the one we did in class on Monday, right?
Oh, 3 is due today. You're right.
Okay.
Well, do you want to see it, or you want to? Okay.
Or I don't know. I guess is there something? Yeah, we can review.
Are you giving trouble?
Yeah, sure. I'd be happy to do review problems, but I don't have anything ready for that.
I should have.
All right. So you got a fixed mass of water M. It starts as a saturated liquid. It's brought to saturated vapor. While its pressure and temperature remain constant. The only work is work of expansion. Derive expressions for the work of heat transfer in terms of the mass and properties.
Oh,
well, you know, we actually did this one. It's a really cool one, so let's do it. Everyone's going to benefit except Graham. Okay, so...
No, I'll still benefit.
Yeah, right, I know, because neither of us remember what the hell happened. Okay, so it starts as a saturated liquid. It becomes a saturated vapor, and its pressure and temperature stay constant. And so we want to start by coming up with expressions for the work and heat transfer in terms of M and properties that are obtainable from the steam tables. Okay, so we're going to be so this is water. And so basically we're using, everything is going to be variables, but we're going to use the variables that you can read off of a table. So we're talking about what are the things that could be useful for the work of expansion, specific volume for a liquid and a gas at that saturated state. And these are all at the same temperature and pressure. So these are all things that you'd read just along a single line in the table. Specific internal energy as a liquid and a gas. Possibly enthalpy. I don't really see how yet, but maybe.
I think we do need the enthalpy if I remember correctly.
And then we definitely, it seems like, are going to need entropy. So those are the variables that we're calculating stuff in terms of. And at state, well, okay, so what can we, I think we can already start to calculate that work of expansion. So the work of expansion is the integral from V1 to V2 of P dV. And V1, it starts as a saturated liquid and ends as a saturated vapor. So this is the mass times little v liquid to the mass times little v gas. We're assuming constant pressure, so we're going to be able to do this integral. And then d big V is equal to m d little v. I guess it doesn't, we've already adjusted these, so we don't have to worry about that. And so this, you can pull the pressure outside of the integral, and this is pressure times mvg minus mvl. I'll pull the m out, and we just get vg minus vl. Okay, so there is the work. And so now I'm thinking, okay, if we're trying to calculate the heat, and we know the work, and we have expressions we can use for internal energy, we probably want to just use the first law to calculate the heat. So the first law says that U2 minus U1, that's the change in internal energy, is equal to Q minus W. State 2 is the saturated vapor, so this is MUG minus MUL. And that's equal to Q minus this expression that we just got for the work. And so Q is equal to PM times the quantity Vg minus VL plus MUG minus MUL. Okay, so now we have this expression for the heat. So part A, we have answers to. Okay, so to do this, we took advantage of the fact that the pressure stayed constant, that it's saturated the whole time, so we know we have expressions for these values at the two states. And we used the first law, and it'll let us calculate the heat because we had been able to compute that integral to get the work. So now we want to show that this process is internally reversible. Okay, well, this is sort of leading us in a way because it told us, it led us towards calculating that heat transfer. And so what do we know about an internally reversible process involving heat transfer, you know?
Sigma equals 0, right?
Yeah, that's exactly right. And so for part B, what we're going to use is that, so we know that the change in entropy is equal to the integral of delta Q over the temperature. Oh boy. Plus sigma. And if it's internally reversible, then this sigma is 0. So now we're trying to come up with what we're trying to do is we have this Q, we have the total heat transfer. We're going to use that in this expression. We know that T stays constant. And so maybe we're going to be able to use that. And, well, we could write this change in entropy as M SG minus MSL, but that won't let us show anything. You know, that's just going to give us a statement involving those. So what we want to do, and this is the only thing I really remember from this, is that we had to use the TDS equations. So let's go to the TDS equations and see what we can do, because the thing is, so let's right away just go, we know we're going to calculate the change in the entropy is equal to the total Q divided by the temperature. And now that we have an expression for Q, we can write that as PM times the quantity Vg minus VL plus MUG minus MUL, and then divide that by T. And we can write this delta S as M times delta little s is equal to all this stuff. All over T. And then we can divide both sides by M. And now we're down to the change in entropy, change in specific entropy is equal to P times the quantity Vg minus VL plus, the M's are all gone, Ug minus UL all over T. Okay, well, we can't show anything yet, but what we need to do is come up with a new way to calculate this delta S, delta little s, and show that it equals this. And one thing you can always use under any circumstances are the TDS equations. So let's write both of those out and see what might be useful. So TDS is equal to du plus PdV, and TDS is equal to dH minus V dP. Just looking at what we have for values, it definitely looks to me like this is going to be the more useful way to go. Although the second one has some things going for it too. dP is equal to 0 because the pressure is constant, but this has all the variables in it that we're trying to come up with, so I'm going to start with this one. And so I'm going to integrate both sides. So integral of T ds from state 1 to state 2 is equal to the integral of du from state 1 to state 2 plus the integral of p dv from state 1 to state 2 the temperature stays constant, so we can pull this out and we get, T times the integral from state 1 to state 2 of ds is equal to, so this is, I'm going to write this as, so this is the change in u from state 1 to state 2, which we can write as what's u at state 2? That's u for the gas, minus u for the liquid. The pressure is constant, so we can pull this out. Now do these integrals and you get that T times specific entropy for the gas minus specific entropy for the liquid is equal to UG minus UL plus P times the quantity specific volume for the gas minus specific volume for the liquid. And now things are looking real good. So now we can divide both sides by T. We get SG minus SL is equal to UG minus UL plus P times the quantity VG minus VL over T. And that matches with this. That problem is cool.
I agree. It seemed impossible at first.
Yes. It did look really scary. Any questions about that? Okay, let's, why not go to some of the ones that aren't, that we don't have solutions to for the second set? We've done this kind of problem a few times. This is just a calorimetry problem. It's called where you're putting stuff together at different temperatures and calculating what the final temperature is. We're going to assume that all of these things are incompressible. It's two solids and a liquid. And what incompressible tells us is that we have a specific heat, and I think we're just going to have to look these up, that's equal to du dt. And so we can calculate a change in specific internal energy as C times a change in temperature. Okay, and since this thing is isolated, we know that there's no total change in internal energy. And so what we're going to do is add up all the changes in add up all the changes in specific internal energy and set it equal to 0. Okay, so we can write this as the specific heat of, well, the mass of the aluminum times the specific heat of the aluminum times the change in temperature is going to be the final temperature minus the initial of the aluminum. And these are differences, so we can just keep these as Celsius temperatures. Plus the mass of the steel times the specific heat of the steel times the quantity T minus the steel is initially hot, 150 degrees Celsius, plus the mass of the water times the specific heat of the water times the quantity T minus, and that starts at 5 degrees Celsius. And all these, since it's isolated, have to add up to be 0. So the specific heat of water in SI units, 4 point, oh, that's grams. So per kilogram is 4180. I think I've always used 4186, but we'll use what they have. So this is 4184. Specific heat for aluminum. Yeah. So I'll call that 900. And then for steel, $4.20. That's like a joke. God's a stoner. God's like watching us with Alice's restaurant on in the background right now, laughing. Okay, and then the masses. So we have 0.1 times 900 times T minus 20 plus the mass of the steel is 0.2 times 420 times T minus 150 plus the mass of the water, which is a lot, I think, 10 kilograms of water, with by far the biggest specific heat, times the quantity T minus 5 is equal to 0. And so we're going to probably end up somewhere very close to 5, I would guess. Let's calculate this. Well, we know that, so it's isolated. So there's no heat coming into the system. We can calculate for incompressible materials delta specific entropy is equal to is it C natural log of T2 over T1?
Now we're testing you.
Yeah. And
Minus RLN P2 over P1.
for incompressible, this for incompressible, it's just this, right?
That makes sense to me.
Yeah. I think that would be for an ideal gas. Okay.
T2 over T1.
All right. Don't try to be all tricky. Okay. So now we're just going to add these up. So what we know is that the mass of the aluminum times the change in specific entropy for the aluminum, because that's the total entropy for the aluminum, plus the mass of the steel times the change in specific entropy for the steel, plus the mass of the water times the change in specific entropy for the water. We know that that has to be, equal to some positive value or 0. Well, how do we know that? Because we know that it's equal to delta Q over T plus sigma, and this is isolated, so there's no heat transfer in. All right, so 0.1 times 900 times the natural log of, for the aluminum, it's 5. Oh no, we got to do this now in, so this is not a difference anymore, so we got to put this all in Kelvin. So I'm just going to use 273. So I'm going to call this 278.32 over 293 plus 0.2 times 420 times the natural log of, the steel started at 150 plus 273, so 423. No, it ends at, they all end at the same temperature, so 278.32 over 423. Plus 10 times 4184 times the natural log of 278.32 over 278. Anyone calculated that yet? Yeah. Okay, natural log. And we get a value of 8.34 joules per Kelvin. So that's the entropy produced.
If you just flip a natural log, it just becomes the sign.
Right. Right. So that's the entropy produced. And then it asks how you know the reverse process couldn't happen. It would be, so the first law never tells you where you start, which way it goes. And so what we would be doing is just, we would still be using the first law, but we'd be going in the opposite direction. So all of these would switch, which would just make each natural log term negative. And you'd get that this is equal to negative 8.34. and that's not possible for an isolated system. Is it possible for a system that's not isolated?
Mm-hmm.
Yes. You can have systems where the entropy decreases. The law just says that as that entropy is decreasing in your system, there has to be a increase in entropy somewhere else, and that increase in entropy has to be bigger than the decrease in your system, bigger or equal to. Okay, well,
You could like just cut off like part of your air conditioning system and right, and then
Right.
say that entropy is just flowing in or flowing out.
Yes, exactly. So, right, you're, yeah, like a refrigerator or whatever is decreasing entropy inside the refrigerator, but it's doing it by vastly increasing entropy outside of the refrigerator. Any questions about that one? We did 4.
The control volume one, maybe? So it's-
Yeah, 6. That's the last one that there's no solution for. Well, let's see how far we can get. Why not? Why not go for it?
If I did it right, it looks like a quick one.
Oh, okay. Okay, so you got a turbine. So, I mean, anytime you're talking about stuff flowing through a device, you know you're going to use a control volume approach. So we have 2 things. You know, we have the control volume first law, and we have the control volume second law. It's steady state. Well, let's just start setting up the first law equation. We almost always seem to use that first. So d dt, this is 0, is equal to q dot minus w dot plus m dot, ignoring kinetic and potential, so we can just write this as h inlet minus h exit. Air and isentropically, we only really know how to do calculations, isentropic calculations for ideal gases. The fact that it's air makes it seem like, okay, let's just treat this like an ideal gas. And so what do we know here? We know so we know that the change in specific entropy for an ideal gas is equal to CV times the natural log of T2 over T1. Is this plus? So tell me what the second term is here for.
RLN V2 over V1.
V2 over V1. Okay, and this is isentropic, so this is equal to 0. And what?
Isn't it P2 over P1?
There are 2 of them. The
That's
second one.
Not on here. Look.
Oh, you wrote okay.
So the second one says is equal to CP, natural log of T2 over T1, minus R natural log of P2 over P1, right? And this is equal to 0. This seems like the one we want to use because we're trying to calculate the pressure at the exit. So we have CP natural log of T2 over T1 is equal to R times the natural log of P2 over P1. So we can say natural log of P2 over P1 is equal to CP over R times the natural log of T2 over T1. E to both sides says P2 is equal to P1 times E to the power of CP over R times the natural log of T2 over T1. And I think we have all these values, hopefully. So we have 6 times 10 to the 5 times E to the power of, for air.
It looks like pi to the power of.
Yeah.
What?
Like the.
Oh, yeah. Yeah. That's not how you spell pi.
P-I-E.
Oh, no. The number, that's not how you spell the math pi.
How you spell a good pie.
Okay, so CP is for air, I think is 718. I think I remember both of those. So CP over R, I think is 718 over 1005. Let's go with that. So that's 0.714 times the natural log of so 1000 K and 700 K. So natural log of 700 over 1100. So 6 times 10 to the 5th times E to the power of 0.714 times natural log of 700 over 1100. And we get 4.35 bar, or times 10 to the 5th. So what was the pressure to start? 6 bar, so the pressure went down a little bit. And what's the work per kilogram of airflow? I guess at this point we're just going to use the first law. It's isentropic, which means there's no heat transfer.
That always means that?
Yes, isentropic means no heat transfer and internally reversible. And so we have that for B, W dot for the control volume is equal to M dot times H inlet minus H exit. And that'll let us calculate. And so how are we going to calculate H? Well, we know that H is equal to so we know that H is equal to, let's calculate delta H, is equal to delta U plus delta PV, which is delta U plus delta R times delta T for an ideal gas. We have the change in temperatures. We can calculate that change in U is equal to So for an ideal gas, delta U is equal to CV delta T if the range of temperatures is smallish. This is a pretty big range of temperatures. We might want to not depend on that in this case, but
I mean, otherwise we have everything to look up in a table too, right? Right, we have a pressure and a pressure and a temperature.
yeah, and so you can look, right, you can look it up in an ideal gas table for air.
Right, yeah.
That's right. So look it up in the ideal gas table for air. Okay, and then that's how you do it. Any questions about that? So yeah, remember that about isentropic because I mean, on a test, I wouldn't try to be like sneaky with it, but these problems, a lot of times they'll say like, okay, they'll give you a hint somewhere that says there's no heat transfer and another hint somewhere else telling you it's internally reversible. And then you need to use that to know that you can use these isentropic equations for an ideal gas.
So yeah, this stuff like in heat transfer, like this stuff all comes up again.
In heat transfer, I think that most of heat transfer is differential equations about careful calculations involving radiation. So that's what I think most of that class is, conduction and convection. You know, we saw these equations that are like differential equations. We're like, not for us. But then you can build these kind of elaborate differential equations that I think you spend a lot of your time on that. But I've never taken heat transfer.
Okay.
I've never taken thermodynamics either. So.
So fluids either. Fluid mechanics.
I have taken a lot of advanced fluid dynamics, but no
introductory.
Right, no undergrad fluid dynamics. So sue me.
That's what I'm in for.
Yeah. I think that stuff is so interesting, though.
I think it's not going to be too bad.
I wouldn't think so.
I don't know,
I don't think there's any reason